Hello, everyone, and welcome to February's Tech Talk. We're excited you're all here today. I'm not going to spend a lot of time going over the features of how you use the GoToWebinar. I think most of you know how, but just a reminder that you all have been muted, and so if you have questions along the way and want to ask our speaker anything, please make sure you use the question box to submit your questions to us. This way we can minimize all the feedback from the various phones and backgrounds people are working in. So questions or concerns, please put them in the questions box and send them over to us. So as Rod's screen says, our Tech Talks are delivered by members for members, and today we're excited that Rod Raybould is here to deliver one. He is an engineering graduate from North Carolina State University and has been involved in the commissioning process for many years. First in the utility sector, in the startup and commissioning of nuclear and conventional power plants, and then in the institutional sector. He has been a member of the BCA since 2005, when he started working in the engineering division at the University of North Carolina, where he directs the internal commissioning team and third-party commissioning efforts. Rod is currently on the board of directors at the Southeast region of the BCA, having also served as the past chapter president. Rod is involved in other commissioning committees, such as a voting member on ASHRAE Standard 202 and commissioning process for building systems. And we appreciate Rod being a liaison for both of those for the BCA. And with that, I'm going to turn it over to Rod and let him give his presentation. And just a quick reminder, also, this is being recorded and you will have access to it on our website under the resources. There's a link there for Tech Talks. You can see all past Tech Talks as a BCA member. The passcode is Tech Talks 2017, all one word, all lowercase. And please go back and see any of them you haven't seen. And as a reminder, if you have not renewed your membership, you will lose access to all of these on March 1st. So make sure you get your renewal in and enjoy today's presentation. Rod?
Thank you, Liz. I'd like to welcome everyone to University of North Carolina, Chapel Hill. We are now about less than a month away from a medical condition here called March Madness, particularly given that our men's basketball team is the defending champions. This presentation was co-presented by myself and another engineer about last April at the State of North Carolina Annual Energy Conference. And I took it, which was really for a general audience, and I narrowed it down and gave it more focus on some technical details that I hope that you'll find of value. So let me introduce you to the project. It's the Medical Biomolecular Research Building that we call on campus MBRB, I think, for obvious reasons. It's opened in 2003 for the UNC School of Medicine. The building size is over 200,000 square feet. And I've listed some of the spaces here. Labs, which are served by 200% outside air handlers of 100,000 each. Offices, also served by a outside air unit, vivarium, auditorium, atrium, and other assigned spaces. So the highlighted areas are the ones that this project had addressed as far as the airflow reduction and what was being served by these air handlers. Just a few pictures of the internal of the site, pictures of the building. We have two auditoriums used by faculty and for student lectures. Atrium. The labs themselves are You see a picture of an open lab bay. There's usually 4 to 6 bays per open lab, and we'll be talking about that in some detail in a few minutes. And we have the single room labs that are typical. They sort of look the same, but the open bays actually communicate air from one bay to another, either through the shelving racks or a hallway. There's sensitive interior spaces such as the BSL2 and BSL3 labs, areas of concentrated heat load. The project background for MBRB was part of a UNC campus-wide proposed energy performance contract. After completion of the investment grade audit, UNC decided to self-perform the energy improvements versus using an ESCO. And so UNC advertised for a designer and selected Dewberry engineers out of the Raleigh office. As with all buildings, particularly as you go back in time, each building has some unique design features. So I've listed some of those here. MBRB, the air changes per hour was around 12 or higher before the project. Terminals were pneumatically controlled by Naylor-opposed blade terminals versus, the more common used air valves that you see in today's projects. Each constant volume fume hood has a dedicated exhaust fan, hard balanced, and that there's no fume hood exhaust terminal. Future installed fume hood exhaust fans provided part of the general exhaust of the open labs, and we'll talk about that a little bit more. Lab office supply airflows are designed to provide makeup to airflows to the labs, and each floor has 2 large open labs of 3 to 5 bays with varying number of supply and exhaust terminals and fume hoods. And here's sort of a graphic from our BAS after the project. Gives you a sort of a sense of the floor plan for this building. You can see the open labs in the dark green, or I guess you might call that Philadelphia Eagles green these days. So project background as far as the goals and objectives, which we would call OPR in the commissioning world. Energy conservation measures, of course, reduce airflows, convert from constant volume to variable volume terminal control, control upgrades, extend DDC controls to all terminal units. There was like 353 of these units to be upgraded. And of course, all this while maintaining an occupied building. With our airflow reduction, our EHS, Environmental Health Safety, allowed us to go down to 6 air changes minimum. And of course, in designing that, you have to take into consideration the cooling or heating loads, such as equipment rooms and corridors or corner office spaces, as far as what the minimum can be taken down to, or whether it needs to be greater than 6 air changes per hour. And makeup air to ensure pressurization is positive, which issues addressed was the building was running negative prior to this upfit and renovation. Office terminal noise and comfort was an issue, probably in some part due to that they were pneumatically controlled. We couldn't see the airflows and were probably excessive in some locations. Thermostat locations, hot spots and core, open lab, environmental, and control. Scope of the work during the implementation. BAS control submittal meeting. I highly encourage on all commission projects, we require in our specs that the controls contractor, designer, other contractors, owners, commission provider participate in a submittal review meeting with all participants there and at the table, so it helps drill down into certain unresolved questions either in design or submittal, and it's a good, very valuable for us. Communicated project schedule. Again, this is an occupied building, so we kept the occupants informed of each step of the project, doing approximately 3 zones at a time. And the strategy will start with groups on lower floors and work our way up to the upper floors, end of duct, to optimize system VP. And again, we had BSL3 considerations, so we had to, no schedule of air handlers could be down, and work in adjacent areas had to be about 2 weeks out to ensure we maintain pressurization. Let's go into open lab controls some. For lab controls on this project, open labs were considered one zone versus subsections or bays. And of course, some of this was just simple mathematics. Some labs had different numbers of supply and exhaust terminals, so you couldn't treat them as a sub-bay. The open labs are designed negative to hallway so that supply airflow tracks exhaust airflow with a flow offset. So I'll talk briefly about the lab controls on the airflow side. It's pretty much straightforward and standard for those that get involved with this. As cooling load increases, the exhaust flow set point is increased from 0 to 100%. The percent cooling signal commands each general exhaust terminal from the min to max of scheduled flows. So you, in essence, have all the exhaust terminals going up and down in flow as the cooling demand of the lab changes. On this project, this is a little bit unusual. When the status of the fume hood exhaust fan is on, an assigned tab exhaust flow is used in the total lab exhaust flow calculations, since we did not have a terminal. And then on the supply side, supply terminal CFM summation tracks the total lab exhaust CFM minus a flow offset. So as the tracking command signal goes from 0 to 100%, the supply terminals would increase from min to max of scheduled flows. So, in essence, you have the entire exhaust terminals operating as one terminal, and all the supplies tracking it as, in effect, one terminal. The last thing on the airflow side, and considering the failure mode, obviously, as it's currently was designed, if the exhaust system shut down, the supply terminal command reduced the CFM accordingly. However, there's no feedback to the exhaust terminals if the supply goes away. So there we deal with that. If the air handler system shuts down, the general exhaust systems are shut down for egress purposes. And we all learn about that need to have that interconnection at one time or another as you work with these research buildings. Open lab controls on the temperature side, can be several ways to approach that. I have 3 options here. One option is have each supply terminal control to a dedicated T-stat. Downside, this can result in terminals simultaneously heating and cooling, particularly if you have each T-stat can be adjusted by the user. So, we got away from that a while back, and then we went to option B, have the BS average all T-stats and provide an average temperature. Compare average temp to a heating set point and provide a common heating percent PID output to all reheat control valves at the terminals. The downside to this is hot water valves at the same percent stroke can provide different discharge air temperatures from the terminal. I have a graphic. I'll show that to you, what that looks like. And then option C, which we use on this project, send the common heating percent PID output to a temperature reset block to provide a common discharge temperature set point. Use each terminal's discharge air temperature compared to the common discharge temperature set point. Command each reheat control valve to maintain discharge air temperature set point. Now, I have, fortunately, a schematic of what this looks like here. Here is and this is sort of representative of our UNC standard control drawings that we provide designers to work from. But the logic in the bottom half here shows where all the space temperatures with the average of all T-stats come into the PID block, and it looks at the heating set point and puts out a 0 to 100% output out of the PID block. Now, in option B, that would go directly to the hot water reheat valves, that percent signal. But we actually, in this project, run it to a reset block. And that can be adjustable. 0 could be 58 degrees, 100% cool. Heating be 85 degrees. And then that becomes a discharge temperature set point. And so that set point is compared to the supply temperature leaving each terminal to control the hot water reheat valve. And so this works, and you'll again see this in the graphic. This prevents heating in some zones and cooling, hot water valve not performing correctly in other zones. An important thing to note here is that we specify the minimum 5 feet distance of the supply temperature from the hot water coil. If you don't tell them that, they'll, in some cases, put right at the coil face, and you won't see even discharge temperature leaving the box. The last item to consider on the temperature side is the T-stat locations cannot always be located from heat sources or from being blocked by obstacles. Everyone's, it's commissioning 101. We've all run into that in the past. To address this issue on this project, one master T-stat was installed on the wall with adjustment and occupancy override, and 2 temperature sensors were installed in the exhaust ducts. And I have a schematic from the control submittal. It shows this. The wall-mounted zone T-stat sensor at the main entrance was always a good location for us to put it there. And then whether it was a 3 or 4 or 5 bay unit, we had 2 exhaust temperature sensors at the ends of each lab. And these were mounted in the ductwork to read the temperatures. And you'll see what this looks like here on this graphic. If you look at the upper left-hand corner, you see the average zone temperature, which is made up of inputs of these 3 zone sensors for exhaust temperature sensors. If you go down below that, straight down, you can see in this lab the calculated effective discharge air temperature set point, which is 71.2 degrees. And then if you go directly to the right along that red line, you can see those boxes are pretty darn close to the discharge air temperature set point. If you come up from those, you can see what the individual supply terminals or PIDs are commanding the hot water valve to be at to maintain that discharge air temperature. It goes from 46% all the way down to 21%. And so, this kind of control we find it works the best. I mean, some of these open labs, I can pull them up and they're all at about the same PID output, surprisingly. Others, like this one, are you have a variance, and there's another one that's even a higher variance. So that's how we do the temperature control. Open Lab graphic is shown here just to give you a sense of how we display that on this project. It's a little bit busy. Any more terminals than this, and we do have labs that have more terminals, we actually put them in a chart or a table rather than trying to show them all on a graphic. Some of the challenges in this project was terminal hot wire reheat valve replacement. Unions were difficult to break and disassemble, and after breaking a few coil piping connections, had a meeting with the contractor to discuss proper technique to prevent further coil damage or breaking off the stub outs from the coils. And then I have a picture of that next. The terminal airflow DP sensor range and accuracy. We monitor terminal airflow DP sensors to ensure the sensor range was adequate, given that the terminal unit had new lower flow and pressure. So, we're concerned about falling outside the range of the flow ring and differential pressure transmitters, but in this case, it all stayed in an acceptable range with a few quarter terminals that were trying to push as much air into the quarters, hallways as possible, and we actually overranged a few and had to back it down some. But something you got to keep an eye on. And this is replacing the old hot wire reheat valves. It sort of comes up, who's responsible for corroded unions and the reheat valve is being replaced, the contractor or the owner? In this case, we pushed for the contractor, and he just had to use a better technique than an unskilled mechanic just trying to, use pipe wrenches and break the unions. As in all projects, you find some things along the way that you really did think of up front. Some of the fume hood exhaust fans that were designed for futures that I've talked about were being used for general exhaust purposes. So what we found with as we reduced airflow, we had extra general exhaust, we could turn off these exhaust fans and use the general exhaust to provide all exhaust from that lab. And doing so, we're able to 36 fume hood exhaust fans were taken out of service. Some of the commissioning findings included incorrect duct stack pressure calibrations of the transmitters on some of the air handlers and general exhaust, resulting in much higher operating stack pressure, energy usage, and terminal control issues. You say, well, that's what you should have done to start with, but the fact that we had a follow-up project to commission the air handlers, we just assume our staff had properly calibrated pressure transmitters in the system, and of course, that's why we commission things. That's not always the case. Commissioning issues logged about 94 items, which were documented and addressed. So the energy savings, the portions here, I'll go through this rather quickly. Electric energy savings, that's a per month bar with a total about 24%. Our steam usage savings came to about 32%. Chill wire savings through the first 12 months was 27%. And here's a table that summarizes all the savings. And when I had to give this presentation last spring, we weren't fully at 12 months. The first comparison months were still, we weren't fully complete with the project. So these are somewhat conservative numbers. As far as cost savings, I have to explain this a little bit. Large campus the utilities such as steam, chill wire, and electricity is provided to the building by an energy services division. And our utility costs are made up of several components. Energy component savings, which you see here. But we also have principal and interest payment has to be made as part of all these steam plants and chiller plants that are carried into our utility fee. And then there's an operation and maintenance fee that's involved. And just because we save energy in these buildings, those debt payments and principal payments and operating maintenance costs don't go away. So it's sort of an unusual situation here. We can only claim the energy savings only and not the other savings like you would if you were directly connected to a utility for electricity and gas. So if I was taking all those into consideration, these savings would be well over twice, if not higher, what I'm showing here, just the energy savings component. Total project costs are shown here for the project. Commission cost was very reasonable on this project. I mean, we're basically just talking terminal units, and it didn't hurt that the commission provider lived about 10 minutes away from our campus, so wasn't a lot of travel time, and he could stop what he's doing as working from home and come over here. Here's a summary of the project costs, energy savings, which, as I said, are very conservative, and the simple payback. Now I'm going to compare that to what a performance contract IGA was projecting. And there is a significant difference here, and I just, in making a cost comparison, you got to keep in mind that the energy performance contractor has many other costs to include, such as financing, active project management. They sort of give us a turnkey project at the end, additional measuring equipment such as airflow stations that go into the annual measurement and verification process, unknowns, and he, of course, has various profit and overhead. So, if an end user like ourselves can afford it and has the staffing resources, you can certainly save a significant amount of money over the entire project versus what you do for a performance contractor. I will say that the upside about a performance contractor is they ensure the performance of the building is maintained. Another set of eyes where, that's sometimes difficult for larger institutions to keep focused and not go on to another project. So to wrap up, I just want to acknowledge again, there was the project team. It was an excellent project team that we put together of, UNC Chapel Hill, various groups here. Our group, we're very active in participating in the commissioning process. We find that we can, achieve a more successfully commissioned project if we're in there and help drive that process to some degree. Our construction management and the engineers, Johnson Controls and System Works, was the commissioning provider. So with that, that's the presentation that I had here, and I was trying to keep it to 20 minutes, went a little bit over. Thank you.
Thanks, Rod. We did have one question that came up, probably should ask you a little earlier, but during the conversion to variable control, were the fume hood exhaust or fans also converted to variable flow?
No, we didn't. The hoods were designed as a constant volume fume hood with the bypass integral to the fume hood. And since there were no fume hood exhaust terminals in the project, they were kept constant volume.
Perfect. Well, with that, I don't see any other questions. It was a great presentation, Rod. We thank you for your time and the Southeast chapter for helping us get this Tech Talk put on this month. Again, next month, it's always the third Monday of the month, and we should be announcing the next one shortly. Excuse me. So with that, thank you, everyone, for joining, and thank you, Rod.
All right. Thank you.